вообще-то.
Добрый вечер.
Добрый день. Слышно что-нибудь?
Да, слышно. Здравствуйте.
Что-то я ничего не слышу.
А я вот говорю, сейчас слышно?
Так, сейчас, прошу прощения.
Раз, раз, раз. Раз, раз.
Раз, да, сейчас слышно.
Вот. Добрый вечер. Да, вас тоже
Добрый
слышно.
вечер, да. Что же он это самое не действовал? Так, нормальный сейчас звук?
Да, хороший.
Мгм.
А точка должна что-то значить?
А где находится точка?
Вверху, ближе к правому концу экрана.
Нет, это сейчас посмотрим, я, наверное, могу ее стереть.
Это клякса нечаянно, понятно.
Да, нет, тут, к сожалению, поскольку Google теперь не это самое, не доска не действует, то я нашел какую-то доску под названием Мира, но она как-то, по-моему, не позволяет, там как-то, чтобы share screen, ну, чтобы можно было, не share screen, чтобы можно было разделить, это то ли я не научился, то ли они для этого хотят деньги, то ли что, в общем.
А почему ты whiteboard не хочешь использовать зумовский?
А что-то он у меня не особенно действует, нет. Я
А,
могу попробовать. Ну, давай попробуем, еще есть время. А как его включить?
ну как-то.
То есть в разделе Screen Sharing надо включить зумовский whiteboard. Да?
Поделиться, да, вы не можете, потому что другой.
Да. Сейчас, вот whiteboard, да. Вот я, пожалуйста, значит, я выбираю whiteboard. И что теперь?
Ну, я теперь вижу тебя и не вижу whiteboard.
Let whiteboards new.
А мне
Ну,
тут
хорошо,
понравился
вот.
такой дурацкий вариант. Типа создать просто файл PDF с белыми листами и на нем типа аннотировать и все. Типа.
Аннотировать. Ну вот whiteboard открылся совершенно
Нет, вот я
нормально.
говорю, use whiteboard classic. И что, вот это и это и есть whiteboard.
Ну, он был, но куда-то делся, ты с ним что-то сделал.
Как?
Нет, ну вот сейчас есть, да, есть.
Сейчас, но мне надо, чтобы он был на том же самом месте, чтобы я мог писать на нем этим самым. Сейчас, ну давайте я попробую. Значит, вот я его перенесу. Вот
Ну
что,
вот
сейчас прямо можно писать.
Ну вот я написал.
Да, а как мне стереть?
А там корзина есть.
Корзина? А где есть корзина?
А вот слева там такое меню открывается. У меня надо нажать на пунцончик с ручкой, и там открываются разные. Ну, есть и стерка просто. Но
Сейчас.
стерка действует только
Да.
на свои.
Меню есть, действительно, оно совершенно в другом месте, но есть, да. Сейчас я сотру.
Да.
О, вот.
Вот.
Хорошо. Угу. А можно, наверное, даже увеличить ширину линии. Да.
Можно, конечно.
Да.
По-моему, лучше, чем Jamboard.
Нет, но я не знаю, а тут можно заранее как бы подготовить что-то, заранее какие-то картиночки, там еще что-то?
Ну, ты должен войти в Zoom, там у тебя есть доски, вот он не случайно же говорит новая или там какая-то, ты можешь заготовить доску заранее. Я это не пробовал, но я просто видел.
Доска, она, по-моему, медленнее, чем Jamboard. Хуже работает.
Медленнее? Ну, Мира будет еще медленнее, это я могу сразу сказать.
Да.
Ну, как она разделяет, я не знаю, но когда она просто пишет, когда просто писать самому, то скорость нормальная.
Ну, сейчас вот было нормально, ты писал, я писал, вроде бы мы видели достаточно быстро.
Да. Нет, но будем надеяться. О, sorry, just I see now the list of participants, so we should switch to English.
Ou en français. Si c'est Matthieu qui est Matthieu Rosenfeld, il comprend français, je sais.
Oui, mais il comprend. Mais Okay, so I should thank Matthieu for allowing me to speak about his. What I will try to explain is just what I heard from him. So just retransmission. Okay, so should we start now?
I think so.
Yeah. So let me start slowly with what. So it's kind of strange application of tools that were somehow developed a bit for Kolmogorov complexity and computer science, just in very classical question of number theory, which, as Matthieu explained me, was opened for some longer than it should, I would say. So the question is about approximations of irrational number. So imagine we have some number alpha, and of course we can, if we want to approximate it by a rational number, we can make the error as small as needed. So if just 1 over 2n, because they go this fractions go with step 1 over n. So choosing m, we can make error smaller than 1/2. But it's better, of course, there is a trade-off between the size of denominator and the precision. So it's better to consider this thing. And we can choose m in such a way that this kind of measure of precision is good. But of course there are good denominators and there are bad denominators. So for example, there is a Dirichlet theorem. So let's say that if this is
Can I just ask that I remember correctly, so that there also there exist this continued fractions that give somehow a better approximation of n squared.
Yeah, so
And
there
then
are continuous fractions, and but they just have some algorithm to find the best possible denominators. But there is much easier thing which is called Dirichlet theorem, which just guarantees the existence of the denominator. So let's say something. Let's make kind of notation. Let's say that this is if it's smaller than epsilon, we say that denominator n is epsilon good for alpha. Now, I don't know what is the standard name for this, but it's more or less just we will say this. And Dirichlet theorem says that for every epsilon there are infinitely many epsilon good denominators.
What is the
So let's
quantifier of
start
alpha?
For given alpha and for every epsilon for alpha.
So for all epsilon and alpha.
For all epsilon and alpha, there are infinitely many good denominators. So
And Dirichlet invented his Dirichlet principle to prove this theorem.
no, it's very strange because I think it's just a specific Russian name for pigeonhole principle in Russia called Dirichlet principle, and probably because of this theorem. But I don't know. I never heard this name in France. So
Yeah, I know. It's specific Russian term. As
I don't know what the standard name.
It appeared in school math Olympiads 100 years ago.
And someone called it Dirichlet principle.
Yeah,
Okay.
yes, someone.
Yeah. Okay, so just let's recall how the theorem should be proven. What do we do? So we can
Can use continuous fractions.
Oh no, it's complicated. Continuous fraction is complicated, and they give much better things. But the
Yeah, I
simple
see.
argument that we can try alpha to alpha.
You already gave a hint. We should, I found it on the Wikipedia. In French, it's called le principe de tiroir de Dirichlet.
Ah,
The principle of boxes of Dirichlet.
Oh, so il y a the nom de Dirichlet. Okay. So anyway, so what we are doing, we just consider number 0, alpha, 2 alpha, and so on, up to some larger alpha on a circle of reals modulo 1. And then there are, if n is large, there are two points which are closer than 1 over n.
Ah, so you want to say that if they're like the 2 points fall into the same part, well, you kind of divide 0, 1 interval into intervals of length epsilon, and you want to say that if there are 2 that fall into the same epsilon, you can take the difference and they will be like close to
yeah. No, it's not very natural to divide them into intervals into boxes of size epsilon, but we can just have many points and notice that if there are more than n points, then 2 of them are on distance smaller than 1n. And so if we go from one point to another, we make some integer number of steps. So there are some multiple of alpha. This is 1 to the n close to integer. So
yeah, that's exactly the same.
It's exactly the same. It's 1 over n good. And the continuous fraction is just if we take alpha is a plus 1 over b plus 1 over c and so on. And if we stop this process somewhere, then we get the best possible approximation with bounded denominator. So it's better than any other approximations with smaller denominators. No, but this is more complicated thing, and it's not needed. So I think Dirichlet theorem should be clear. And now imagine that we are more restricted. So we allow only some denominators. So Dirichlet theorem and continuous fractions give us good denominators, but what if we don't want to use all? So for example, let's assume that we allow only powers of 2. And the question, is the Dirichlet theorem is still true in such a stronger form that we can find epsilon good denominators of which is a power of 2? What do you think?
Maybe yes. Why not?
No, but what does it mean that if we allow only powers of 2? If we have some alpha is a binary fraction, something like this. If we take a denominator which is 2 to the power of k, we just move the binary point k times right, k positions right. And so the distance to the closest integer will be just this part. And it is very good luck if it's very small or if it's very close to 1. This means that we have either many zeros in our binary fraction or many ones. So if we look at the binary fraction like 0, 1, 0, 1, 0, 1, 0, 1, and so on, which is 1/3. So whatever we can get by considering the tails, it's just either 1/3 or 2/3. So if we have such a bounded, such a small set of allowed denominators, then there is there is some alpha which doesn't have good denominators in this sequence. And this gives us a theorem. And this is a theorem from number theory, and unfortunately I did not do my homework correctly, and I don't know who asked this, who solved this, but it was, Matthieu explained to me that it was for some time, it was a question. And later it was answered. And imagine we have some sequence of denominators such that grows fast. For example, we can assume that each time the denominator doubles. Of any integers, but we will use even denominators. Then there exists some epsilon greater than 0, and there exists some alpha such that none of n alpha is epsilon good for none of ni is epsilon good for alpha. So, for example, for this specific sequence of denominator, we have seen example of alpha, which is with very specific epsilon, just 1/3. But of course, if the sequence of denominators is other sequence, we don't have such a good explicit example. But there's still a result like this. So maybe someone has some idea how to prove it. We can try some simple tricks.
Well, maybe we can first understand how it works if I have like powers of 3, powers of 4. And it seems
No,
like
if we
it's
have
good.
powers of 3, we can use ternary fractions. It's quite
you
easy.
just- And if I just take, for example, in your example, I don't understand. What if I just take one? Well, I don't know. What?
If you take what?
So, for example, in a ternary, I can take just 0, 1, 1, 1, 1, 1. I mean, in ternary
Yeah.
expansion.
Yeah. It's just maximally
I just
fast.
need the
It's
number
1/2 actually.
that I just need some infinite expansion such that it's bounded away from 0 and from 1, whatever place you start.
Of every tail is not close to 0 and not close to 1. Not close to 2, not to maximal 1. So there is the problem appears when this ni are irregular. Then we don't know, because actually if they are powers of 2, they are somehow related. The quality of these denominators are somehow related. If we have a good denominator, very good denominator, then the second one is also good. Not that good, but just twice bad, twice worse. But if we have
So maybe you
arbitrary
can
number,
tell then what is the full condition under ni for which this holds? I mean, so it's just powers of 2, or it's specifically about 2, or there's
no,
something? So if I
actually,
have
what we need only that in any interval between, I don't know, n and 2n, we have O of 1 denominators.
So 0.9 to the n will not work. I mean, the powers of 0.9.
No, 0.9 to
Oh,
the n
sorry,
converts to
1.9.
0.
1.9.
1.9 to the n theorem can be applied because they are just, I don't know, 100 denominators in this interval.
Yes.
Yeah. So we can consider power of 2, 3, and 5, for example. That's also okay. So we can do many things, but still there should be rare. They should be rare, and actually they should not be too many of them. Okay, but the simplest idea is to try something, to choose something randomly. Just let's look. Imagine we want to take alpha. We think about alpha. So, and we want some denominator n to be bad. Then alpha should be far from 1n, 0, 1n, 2 over n, and so on, up to 1, which is again 0. And it should be not here alpha which are not good for us. So if we fix some denominator, this denominator excludes n excludes epsilon fraction of all alpha, or 2 epsilon fraction of all alpha.
If
So
we're
if
going
we have
to sum up epsilon fractions for infinitely many denominators, then we're in trouble.
Yeah, that's exactly why it doesn't work. The union bound doesn't work, because we have infinitely many denominators. So if we have a small epsilon, then we are not in good shape. And there is actually it's somehow close to situation of Love's local lemma, because if we have different denominators, we have different types of excluded sets, something like this. So, and if then we have even very small one and so on. So if we have various denominators of drastically different scales, they are somehow independent events. So this is close to situation in Love's local lemma. We have many conditions, infinitely many conditions. Each of them excludes some small fraction, but constant fraction. But still they are dependent, only the dependence is limited. And then we can avoid all of them by virtue of Love's. But this is a too complicated thing, and we want to give a simpler proof. And the simpler proof, it's very nice. It's it can be explained in terms of some Olympiad problem, and also there's Olympiad problem has a very nice solution by Joe Miller, and we can apply it directly to get the proof. Okay, so now it's a good place to stop and to ask questions before I'll try to go to the solution. If it's not, something is not.
The numbers n and I are arbitrary. You're not assuming that they're co-prime or
No. This is exactly what makes things difficult. Why for powers of 2 it was easy, but for arbitrary number it's difficult.
Or maybe just, can you say who proved it first or something like that, if it's possible? I mean, so I see that it was a question from Erdos in 75, but who solved it? I mean,
that's a question. I don't know really. We should ask Matthieu. But,
well, I don't know. Like, it was open for 30 years, and then somebody came up with this Olympiad problem, and
no. It was. I think they proved it maybe using Love's local lemma or whatever. But the proof is so easy. But maybe we should first start the proof. And the proof.
Well, you said it's time for questions, so I asked the question.
No. The question's about what was already said. No. It's a valid question, but just I don't know. So
Matthieu is saying that it was a question from Erdos and it was solved by Peres and Schlag in 2007 with local lemma.
Oh, but when it was solved?
2007.
Oh God. Okay, so it's yeah. No, but no, you will see now how easy it is. So just let's go to the proof. I will try to. So let's construct our alpha. So we imagine we fix. Fix the denominators and 1 and 2 and so on. And k. And let's construct some alpha just by trying bit adding zeros and ones bit by bit. So we just construct an infinite binary string. And our goal is that when L bits are constructed, we no guarantee that alpha is epsilon bed. Epsilon is some constant we need to choose. Yeah?
For the first omega L denominators.
For the first, yeah, L, not omega, just L minus some D.
I mean,
So this is some parameter which we will choose later. And epsilon is some parameter that we will choose later. So what does it mean that we can fix L bits? We know that there is interval 0, 1, and there is some interval of size 2 to the minus L.
Yes.
And if we just now increase our L, we should divide this interval in 2 halves. And the goal is to avoid one new denominator. So each new bits in alpha takes into account one more denominator. And so we
So
deal
you
with...
somehow want to start, but you have to somehow cleverly start then to choose the first d bits very cleverly somehow. I don't.
No. The first d bits are chosen completely idiotic way, arbitrary. We just need to start considering denominator, not too fast. So we need some kind of gap between the so we have this interval, so we have some kind of freedom, and we need the denominator be quite small compared to the thing. But let's see.
Wait. Can you specify what means? We know that alpha is epsilon bed. Exactly. So it means that for any number that has this L bits, they are epsilon far any.
We know that every alpha in with this L bits is epsilon bed.
So it means that this interval 2 to the minus L is, it's all far from all the.
It's all completely free from bad numbers which are close to. Okay, let's draw something. So we have this kind of multiples of. There are multiples of NL minus D. And our interval should be far from all these things.
Yes.
And our assumptions guarantees that this in our picture, this step is much bigger, longer than 2 to the minus L thing.
Pasha, can you remind what means epsilon bed?
Epsilon bed means that alpha minus n, my epsilon bed for denominator n means that n alpha is far from all integers.
Mm-hmm.
Okay, and now I think maybe now it's time to explain the Olympiad problem and the game, and then we will see how they are connected. So we make a digression now, and we consider the game. The game is
Sasha,
played
you can make a new page and not wipe out.
Okay, how can I make a new page?
In the right bottom corner, there is a
Great.
plus.
Plus. Oh, yes, indeed. And I can even move to the previous page. Yeah.
Yes.
Very good. So the game is like this. There are different languages. So let me say that there is a binary tree, and there is a dangerous criminal in the root. And the criminal wants to escape by going to infinity. And there is also another player is police, which wants to prevent this. And for that, they can block some vertices. This way is now impossible for the criminal. And so the criminal makes a move, and or it's not important who starts. Police makes a move, blocks some vertices, and then criminal makes a move, and so on. They alternate. But of course, if police blocks everything, it's trivial. So police has some restriction. Only I don't know 100 vertices can be blocked at every step. And second requirement is the police is afraid to come too close to the criminal. They should be at least 20 levels ahead from the criminal. So, of course, it's important that the total number of vertices on these levels that should be blocked is much more than 100. So the police cannot block all the paths. But still, it's not. And the lemma is that criminal can escape. And this is a game with full information, of course. The criminal sees where the policemen are. No, actually, it's not important if you can prove instead of 100 vertices with 10 vertices, and instead of 20 levels with 1,000 levels, it will be okay for our theorem, just constants will be worse. And so I guess maybe someone already knows how to prove the lemma. It looks so obvious that you cannot really, the police is very weak.
I don't know, like you should probably go into direction where the sum of weights of police vertices is smaller than something. I don't know.
No,
I mean,
excuse me, I have a question about the rules of the game.
Yeah.
So on each step, police is allowed to block several vertices by this rule.
Yeah.
But what the other player is allowed to do? It is allowed to make only one step upwards.
Only one step.
Only one. Okay.
Of course, if he can make many steps, it can just go free very far away and where there is no police blocks. So the game starts in U every time. So of course it's
Yeah. So okay,
it's
so you
trivial.
just try to maintain the invariant that, like I don't know, that's the every police vertex, it's like, I mean, how to explain it? I mean, so that
Yeah.
we can
Every
assign a weight to
block
every
is a
vertex, which is 2 to the minus depth of this vertex from the current position of the
Yeah.
criminal.
Okay. That's so if we have some no, of course the blocks which are behind or on aside are not important. So at every point, the criminal looks on the future, and some
Yes.
part of this future is blocked.
Yes, and we want to maintain that the sum of these weights of the block vertices is smaller than, I don't know, 1/10 maybe.
Yeah. So
Then I can say what is strange in with this plan. It seems that when you go to the left or to the right, the best thing you can hope is to maintain the fraction of the block paths above you. Because when you go one step upwards, in some sense, the things are getting worse because you approach the blocked vertices. So the damage of these blocked vertices becomes twice more. On the other hand, you choose one path of the two, of the left or the right. So you can get rid of a half of these dangerous blocked vertices. So it seems that when you go upwards, you cannot make the things better. You can only maintain the percentage of the blocked paths, and the police will just add little by little a new blocked paths, and
Yeah, that's true.
if we wait long enough, it will kill all our. So the natural idea is just to go in the direction when less spaces is blocked, and the space is normally measured by just the probability or just fraction in the tree or probability of bump into this place. But the problem is that if it's equally distributed between left side and right side, then we don't have any reason to choose one of them. So we choose some of them, and then we have half of the blocked space. But now the obstacles are closer, so the space is multiplied by 2. Because
the police is also adding this.
And what is worse,
vertices
the police adds new vertices. So they also again add a very small new part, but this part is added to the already existing ones.
Too bad.
Too bad. But
maybe
still,
you should define the weight somehow very different, not with 1/2. Well, does it make sense?
No, of course it does. So what should we do, Sasha? Say it more precise.
No. I mean, I just try to consider instead of 2 to the minus k, where k is the distance, some other alpha.
Let's take some alpha, not alpha. Let's say some c smaller than 2. I don't know, 1.5.
Yeah.
And then or 1 point, I don't know. Maybe we should choose it later. But then if something is k levels apart, the weight is not 2 to the minus k, but just c to the minus k. So we somehow make some discount. Not discount. It's bigger than the actual part of the space.
Yes, but I mean, then the thing that then
Let's see what happens then.
you take the smallest half, but you multiply it by not 2 but 1.5.
Yeah. Now, when we if this weighted I don't know obstacle size. size is now multiplied, divided by 2 if we take its smaller part. And then when we
Yeah.
move, it's multiplied by 1, by c. So it's only 3/4 of original obstacle weight aside.
And we can maintain that it's smaller than constant even when we add some small constant.
And then we add something, and which is still we have 100 times 1.5 minus 20. So if we need it to be smaller than v. So we want the weighted obstacle size should be smaller than 1. So we need that this is smaller than 1 plus 3/4 plus 100 times 1.5 minus 20, and it should be smaller than 1. So this is the main technical trick, and this is what is done by Joe Miller in his paper on two nodes on subshifts. Then he constructed sequences without forbidden factors, and this is the same trick. The obstacle is taken into account with some weight which is bigger than its size. And in this way, we get. No, so I don't know whether. Of course, I heard about this many times, but if Sasha, if you haven't seen this before, then you probably can confirm that this is a natural idea, and then it's easy to.
No, I can say that I have here this type of argument, and I don't think it is a natural idea. It's a ridiculous idea. It's still very strange that it works.
Yeah, but if you
my interest is to say that it's not natural. It's just that
no, you have conflict of interests. So
Yes.
you want to present yourself as someone who invented a very clever idea. But also you may present yourself as someone for whom everything is trivial. So I don't know what you prefer to do, but anyway, this is the story. But no, but if you think a bit more, if you will give this problem to a high school students, they probably will invent a completely stupid solution, but which still works. So if you now want a stupid solution, not a serious one, what you will do?
No, but that you have to be as clever as a high school student.
Or as stupid. And let me say this solution. But imagine there is just I don't know, few vertices, not 100, but 5, and they are very far away. It obviously should be safe.
Yeah. Okay.
Why they are safe? Because if they are very far away, they will still remain far away for a while. And so we can make, we can postpone, we can still avoid all these bad things. So let me say another. So imagine that we make games only more difficult. Our enemy makes, I don't know, 10 moves. And we even don't see these moves and need to move blindly. So we can go wherever we want, and on level 10, while the enemy makes 10 moves. And then these moves are open to us. And so they are At least still they are 10 levels apart.
So you want to explain that we can allow the criminal to make not one step, but say 10 steps. In 10 steps.
Just
Right.
our criminal can wait and be drunk for a while and then catch up when the police makes 10 steps.
Mhm. And then he can make also 10 steps.
Yes, not exactly drunk. It should make some 10 steps, but make them arbitrary. Don't worry about the police.
Do you mean that he can also have like a vision? He can only see 10 levels ahead, or something like that.
No, yeah. So then after these 10 steps, he's here, and then he sees 1,000 obstacles because each times we have 100 vertices, and so there are 1,000 obstacles. In the worst case, they are all on the level 20. So he can find some vertex on level 20, which is not damaged. So all existing police obstacles are not above this vertex. And so then he decides to go here and forget about what police is doing. And again, police does something, but of course now it's important only what it does here. But still after it's all 10 levels ahead, so there are again 1,000 possible bad vertices, and we can choose one which is not affected. So you see
Maybe,
that there is.
I don't know, can you just say the same but without these 7 moves? I don't know. So it seems like some cheating, or I don't know.
No, we need to
In
make
the simpler initial statement of the program.
No, we need to group our moves somehow. I think it's important. So we just divide the things into blocks of 10 things, and then make our things more difficult. We just get information only after the step is finished, and have to move before.
Sasha, the criminal strategy is to react only on obstacles that were 10 moves behind him. And he does
Not really, because when he chooses this path, safe path, it should also be sure that previous obstacles, which some of them are further, are not on this subtree. No, you cannot look only on close obstacles because they can become close suddenly. You can somehow you can be short-sighted, близорукий, in the sense that every obstacle seems to be beyond level 10. Whatever obstacle you have, you imagine that's on level 10.
No, okay. Can I ask simpler question? So if the
Yeah.
police is so this number 10, where it appears from? If we have 20 levels and we have to divide it by 2.
Yeah,
somehow-
we need that 20 levels is divided. No, we don't need to divide it by 2. We needed that we can subtract 10 and still have 10, and 10 times 100 is still smaller than 2 to the 20 minus 10. This is what is important.
So can you tell, so let's say the game starts with the criminal, what he does.
He just makes 10 steps, ignoring everything.
So whatever in these 10 steps police does, he just moves.
He just
10
ignores
steps.
this and will consider it later.
Yes,
After
and
10
then
steps,
after
he
10
sees
steps,
thousand blocked vertices, and all of them are at level at least 20. So he assumes that they are on level 20,
yes. Wait,
and then decides.
because it's wait, because it's 100 times 10. I just want to understand how the numbers
Yeah.
work. Yeah.
Yeah,
So
because
he sees it
each
most
time we have
1000 block vertices. Yes.
yeah, and still for the criminal wants to plan his move for the 10 next steps in advance, ignoring what at that moment this move
And
do not
he chooses
depend.
a vertex on the 10th level of for which there is nothing,
So which is completely free now.
which is completely free.
Of course,
And
it
so-
won't be completely free when he comes there finally. But
What?
again,
When he comes there, it won't be completely free, but it's
free,
still there will
but
be
it
like
will be
at
still-
most
still-
1000 vertices and 10 layers
at least
ahead.
10 things ahead.
Yeah. Okay. And you just want to say that even if I don't put like this 1000 vertices all on the 12, on the same level, it then can only be worse.
Yeah,
It's still there exists
no,
a vertex
actually
on
there will
the-
be 100 vertices on levels. It could be 100 vertices on level here. It cannot be all on this level, but it's even
Wait,
even
wait, wait.
more.
Can you say formally why even there will be, I mean, maybe it's a stupid question, why there will be 3 vertex on the 10th level?
No, because if we take 1000 vertices on level more than 10,
Well, each of them
each of
covers
them
it
can
one.
occupy only
Yes.
one
Yes,
sub-tree on level 10. So some
Yes,
sub-tree should be free.
Okay.
Yeah, so I don't know, maybe as an expert in high school Olympiad, you can say whether this solution is more chances to see it if we give this problem, or maybe some other solution will be developed. But
I don't know. It seems like there's infinite tree overall, so it's hard to judge. It's not really like a math Olympiad.
so you think okay, infinite tree is frightening.
Oh, well, yeah, but this solution, yes, it's easier and more, yes.
But of course, if, for example, if you know what is Hausdorff dimension, then the idea to choose another base is quite natural, because it's exactly how we measure the size of the covering when we define Hausdorff dimension.
But okay, how we derive these denominators from that? Should be somehow.
So now the lemma is clear, and we can return to the denominators. Yeah.
Yes.
Right.
Okay. So let's try to go back in this system. And so now what are our players? So our criminal constructs the alpha.
Yes.
And our police just criminal adds bits to alpha, and police adds denominator. So what is important, that police adds one denominator at a time, or constantly many if we have of them. And second, that it makes it with some delay. So if we have L bits, we consider the denominator of size nl minus d, which is 2 to the d bigger than the size of our interval.
What?
No,
There is some inequality here.
No, that's what I said, that we consider the denominator with some delay. So when we already have L bits, we consider the denominator which is constant times smaller than 2 to the L.
So you can, there is possibly a sign of some inequality, which is not written here. That L minus D is at least this or something like that.
L is D at most 2 to the D to the minus L. Oh, no, not minus L. Sorry. How I erase. It's. So it should be. It should be 2 to the L divided by some constant 2 to the L divided 2 to the D.
So 3 to the powers of 3 do not work. Or I don't know.
No, powers of 3 they do work because we just should change the numbering. We need that between n and 2n is only constant number of denominator or just one denominator.
Well, I just see the inequality written, or maybe it's my fault because I asked you to write some inequality, and now it's misleading me.
No, okay. So we introduce the denominators only when they are small compared to 2 to the L. So new
Well,
denominator.
then erase this inequality. I don't know, because this inequality says that
Wait,
the
it's use
denominator
wrong
is small.
numbering. It's use wrong numbering. Yeah, indeed. Yes.
Delay L bit. So criminal makes the first, I mean, or I don't know, what does it mean?
No,
delay L bit?
criminals make some first step, but at that point, actually, police doesn't do anything even. But let's look what is the role of epsilon. So let's look again on our picture. Let's draw a bigger size picture. So we have some interval of size 2 to the minus L. And we have some multiples of our new denominator introduced on Lth step. It's bigger than some constant times 2 to the minus L. The step is bigger than some constant times 2 to the minus L. Or denominator is smaller than 2 to the L.
So, I mean,
some
that I'm
constant.
asking. So this argument now doesn't apply to power of 3, when these numbers are powers of 3.
No. If we have powers of 3 in every interval between n and 2n,
But
we
I
just
mean, so
keep-
what you're saying, the denominator whose index is L minus D is at most 2 to the L or something like that by some constant.
Okay, no. What I'm saying is not correct. So we don't introduce new denominator on each step. We just introduce denominator of size between 2 to the s and 2 to the s plus 1, we introduce us on step s plus d. So we are slightly ahead of our denominators. So if there is no power of 3, for example, in this interval, we don't introduce any new denominator at all. Что-то, Саш, я что-то это самое. Что-то я неправильно отвечаю, но скажите еще раз, задайте еще раз.
Well, I don't know. So I don't know. The game will be exactly as defined on the next slide. I mean, on the second slide, or there will be some
but new
modification.
denominator will not. If the denominator grow fast, then on some steps no denominator will be added.
Yeah, but that, I mean, I'm just asking. So in that game, there is some delay. There is some requirement that police has to make steps, it has to forbid some nodes of the infinite tree, but with 20 layers ahead or something like that.
Why we should be ahead? No.
No,
This
but
ahead
so I
delay.
guess. So what? How many layers? How it's defined? Like depending on what
Okay,
is the.
let me say like this. So it's not really important that this is much bigger, this step. Let's just, it's actually, but let me just draw a picture. So what is forbidden really are epsilon fraction of the space near these denominators.
Well, yeah.
And what does it mean? It means that in our binary tree, which starts here and goes like division, binary division, all the intervals which intersect this bad interval are now forbidden. And they are all grouped just around one position. And so, if epsilon is small, we can make only 2 or 3 of them forbidden. So not even 10, 100, only 3 of them, if epsilon is small. So if this
So
step
epsilon
is,
is related to this delay d. Yes.
yeah, so for delay d is actually very simple. Let's require that this one of the current denominator should be bigger than the size of the interval, or maybe twice bigger than the size of interval. Then only one point can go inside the. Only one actually multiple can be in our interval.
It is unclear in what place you choose epsilon. Is it chosen in the beginning or what?
No, now I say, now it's time to choose epsilon if we want that it will be 20 level apart only. We should take epsilon is just smaller than 2 to the minus 20. Or
I see. It related to this.
Yeah. So the first restriction why we delay is needed to avoid the case when there are 2 multiples in the same. Two multiples are dangerous for us, and this can be avoided if this length of this interval is just twice bigger than the size of this interval. And then we need to know that the obstacles are only very few of them. So on the level 20 level apart, we have 2 to the 20 intervals. And we need that this point can damage only 2 or 3 of them. So we need that 2 times epsilon should be smaller. So epsilon times our size should be no, more or less epsilon should be 1 over 2 to the minus 20 times one more constant, because this is bigger than this size, something like this. So the first is not important really. We just need to it's useless to increase the denominator, to delay the denominator much bigger, for longer, because it doesn't help us. Still it's possible to have one bad point here, and then the epsilon should be chosen in such a small way that it invalidates only 3 or 4 intervals on the level to 20 layers apart.
Well, let me try to say it
Yeah.
again. So,
Yeah.
so we consider this game. I
Yeah.
don't know, let's say with 100 nodes in 20 layers ahead. I mean, assuming that, I guess this is some small constant of one of the number of denominators in the interval n to n. Well, I don't know, let's say maybe it's 3, it was 3 or something like that.
3 or
Maybe
4 are
it's-
completely okay. 100 has big.
So yeah, and we have a strategy of a criminal that wins in this game. So we assume, well, I guess we
Yeah.
assume that, and we give a then we give some strategy of a police.
Yeah.
And what we want to achieve is that police somehow marks all epsilon good vertices or something like that.
No, police marks all the numbers which are close to multiples of. So at each step of the police introduces some new denominators. If there are finitely many of them in this interval, okay, let them be finitely many.
Yeah, I mean, I just want to say, like, what? So I'm saying that, like, police tries to achieve something that guarantees that we construct alpha, which is epsilon bet for every and denominator. Can we say,
so
like,
let me say it more clearly. So police considers all multiples of the new denominators.
No, you are describing a strategy. I'm trying to say what the police tries to achieve with this strategy.
No. I describe some strategy for the police, and the existence of counter strategy for the criminal would imply the existence of good alpha. No, I don't try to, no, it's just, we know that there exists a winning strategy for criminal. And this strategy will be used to
so
construct
the first
alpha.
question, so this strategy of police that you are describing, it depends, it looks what the criminal does or not.
Yeah, it depends on what criminal does. Because it's very interesting in the current interval chosen by the already done choices by criminal.
Okay, let me try to say, because otherwise I'm confused. So there is a notion, I guess, hidden notion here in your argument, that the vertex of the tree is epsilon good or epsilon bad. It's epsilon good if there is a...
With respect to some denominator.
With respect to some denominator.
If the corresponding interval on the real line comes epsilon close to a multiple corresponding to this denominator.
Okay, well, yeah, okay, so we will... Okay, so when n1, when is n1 added? On which step?
So denominators between n and 2n are added when the size of the current interval is about 1 over n.
I said the current interval.
There is a group of denominators between, I don't know, let's say between 2 to the s and 2 to the s plus 1. These denominators are added on step s plus small constant, like 1 or 2.
When the depth is already what? S plus the small constant?
When the length of the game is s plus some constant.
Okay. And why this adds at most 100 nodes 20 layers ahead?
Okay, because there are, I don't know, at most 5 denominators in this interval. And if we look on the intervals on this current position of criminal, actually only one multiple of each denominator matters.
Why this whole interval cannot be close to some denominator?
Sorry?
Why it cannot be that there is this is 2 to the minus L is much smaller now than epsilon. Why it cannot be that there is some denominator?
Epsilon is a relative thing. We take a multiple of some denominator and take epsilon fraction of this length. So the size of step is approximately 2 to the minus L. So when we multiply it by small epsilon, we get something which is a small compared to the size of the current interval, like 2 to the minus 20 of the current interval.
I don't understand what you said. I imagine that the difference is additive, not multiplicative.
No, the difference is additive.
Yes, and you're saying that it's multiplicative now.
No.
Somehow you say that this epsilon becomes small. I don't know, so it cannot cover all current intervals.
So let's just picture. What are the alpha that are for which some denominator n is epsilon good? It's like this. We take all the multiples of 1 over n.
Yes, and take the 1 plus epsilon minus plus epsilon 1 minus epsilon around every point.
Not. We take epsilon part of this interval, of course.
Well, can you explain this?
We compare alpha n. Alpha n should be far, for epsilon far from in integer numbers. So here the alpha n is integer. In these points.
So you say that you have to divide it by n. So you take plus epsilon over n minus epsilon over n.
Yeah. That's what I showed here. That for every denominator, we eliminate only epsilon small fraction of the entire space.
Yes.
But
yes,
this becomes more and more dense, but still small.
Okay, so you say I have after L steps, there is 2 to the minus L.
Yeah.
And in that case, you want to consider
vertices on the level L plus 20.
Yes, but
there are some, we have million intervals here. And some of them are in dangerous zone. They're epsilon close to the denominator. But if epsilon
But
is...
for denominator,
Yeah?
that's
Okay. Just
yeah, I
ask-
mean something. I mean, just it's hard to understand completely, but I see where it's going. Yes, somehow it's just have to think.
No, it's because I'm explaining a stupid way. It actually, there is nothing non-trivial happening, actually.
Well, I mean, I just can't follow. I mean, is it steps ahead or steps forward? Like, I mean, I don't know how the numbers are related. Why it's this condition is where this condition is used. Where is
No,
this?
let me say how the numbers are related. First, there is number L on which the game is played. And this corresponds to the intervals of size 2 to the minus L. And then
Yes, we want to maintain some invariant or something that this interval is epsilon far from all.
No. When we say we mean with our strategy will maintain some invariant. But this is the business of the strategy. We don't maintain any invariant. We just explain how the polis plays. And all
Yes.
the invariant maintaining things is just the strategy problem.
No, but I want to understand. So this first L bits should be already fine for some intervals. So we don't have to, sorry, for some denominators. So we don't have to care about them.
No,
I mean,
after
criminal.
L steps of the game, then the first bits are fixed. And the
And then we kind
denominators,
of just erase some number of, we forget about
the
some number of denominators. We already
denominators of
dealt
our
with that.
previous denominator of our previous group are now, we don't consider them at all. We consider
Yeah, because
new
we
group
already
of
dealt with them. They cannot be epsilon
Yeah,
good
they
for our
cannot be.
epsilon.
If the criminal isn't caught yet, they are.
That's because all these points, I don't know, with the step 1 over n for these things that are all far from this 2 to the minus L.
They are not all far. I said wrong. So they are treated on the previous steps. They are taken into account in the polis obstacle already installed. So we are
Well, but
now.
what is this means? That so this all the numbers in this 2 to the minus L interval, they cannot be epsilon n divided by n close to a number of the form I divided by n for these denominators that we have already treated.
No, that's no. Some we considered smaller denominators on previous steps, and some of them already created some obstacles, which were installed by police on the previous steps. But we don't delete the obstacles. We just add the obstacles. Police at each step add the new obstacles. And new obstacles are corresponds to new group of denominators.
But I don't understand, like,
It's because I'm
why
explaining.
does all this supposed to prove that there exists alpha, which is epsilon beta for all the denominators?
Because there exists a path which avoids all obstacles installed
And
on all
obstacles
steps.
should be the idea should be that the police should somehow mark all obstacles,
Yeah.
all epsilon good vertices in some sense. I don't know. So
No, for every denominator, police should create obstacles that completely guarantee the path from going into epsilon good zone. That's true.
epsilon good zone. Is there a definition of an epsilon good zone? No, I'm sorry. I mean, yeah. I mean, let's maybe I should just let's.
No. It's trivial thing which if I cannot explain, it's my fault.
No, I mean,
Maybe
so the problem is that the argument should be like
Sasha
there. So in this
Kazachinsky,
game there existed. Yes.
look, if we have defined L bits, we are living in an interval of the length 2 to the power minus L. And good zone means that some denominator guarantees epsilon approximation. And it is possible if epsilon is, as is written, 2 to the power minus 20, there are very very tiny fraction of our interval of length 2 to the power minus L. There are 2 to the power 20 subintervals of length epsilon. And because only constantly many denominators are involved in this step, we can block only small fraction of intervals. It completely corresponds to this picture with tree and blocking vertices.
No, I'm sorry. It's a simple thing which I said in a stupid way. But what is important? Maybe just I want to say one thing again. So the previous, it's not true that what may be the source of problem. It's not true. And after L steps, we are safe with regarding to the first L group of denominator. It's not true. And indeed, in terms of our policy, after L plays the obstacles installed on the previous step can still be important for current situation. What we now count is how many new obstacles police can add at a given step. Oh.
Okay, well, but I mean, formally, at least when you like add the denominator, it means that police marks all obstacles that are currently can be of interest. I mean, that they can affect the situation. Maybe it doesn't affect like alpha is starts from the other sequence of bits. But when the denominator, we add all vertices such that if we come to these vertices, it is possible to have alpha which is epsilon close to these denominators.
Yeah, if we mark all vertices on the level L plus 20, which is dangerous with respect to current group of denominators and epsilon.
Yeah, but so I'm saying, so at least when there are already L steps of the game, you want to say that for some denominators, already all obstacles that can affect the game are added for these denominators.
Yeah.
It's not that we forget about them, but the obstacles
they are already added.
And this corresponds to the game because in the game, obstacles do not disappear.
They do not disappear, they are just accumulated.
Yes.
But
and then you want to say...
at each new step, we add only obstacle that corresponds to new denominators. And we are a few new denominators. Each of them can intersect our interval of size 2 to the minus L only in one point. And affects, if epsilon is small, like this, it affects only 2 or 3 intervals on the level L plus 20.
But still, I don't understand, because you're saying because intuitively it means that for police, so it's easier for criminal, the slower police at denominators. On the other hand, if the criminal does already many steps, then and I have a small denominator, then I can cover all this interval already.
No, no.
Really?
What I am saying, it's okay if police considers the denominator not depending the ordinal number, but depending on their size. So the size of denominator considered on the current step is just the numbers which are just bigger, a bit bigger than 2 to the L. If there are no denominators like this, the better. So if the denominator grows
So on the
fast,
L step, I consider numbers from 2 to the L plus 20.
no, like 2
2
to the L plus
21.
1, 2 to the L plus 2, or something like this. So on step L, when you have interval of size L, you consider the denominators in this region. And because you use epsilon like 2 to the minus 25, I don't know, then each of them, if you look, our interval of size 2 to the minus L is divided on 2 to the 20 intervals of size 2 to the L plus 20, then each dangerous zone can occupy only 1 or 2 of them.
Yes, I think.
And so the new obstacles added by the police, there will be not many of them.
Yes, I think I
Oh,
get it.
okay.
But I mean, in my opinion, it's just easier to just tell this proof, this cool proof without this game, just directly.
No,
guess.
without the game, then we somehow intertwine the strategy chosen for the game, and which can be different, as you have seen. We have at least 2 different strategies for the game. And then...
Well, they give one possible strategy or something. I don't know. It doesn't matter.
No, I don't... I think that separating these 2 things makes things easier, but I don't know.
No, I mean, it made for me much more difficult, to be honest.
No, maybe now you see the problem which you would have not seen without this thing. But okay.
Probably the second strategy can be this, where you can just try to maintain an invariant that there is something. So 10 layers ahead when there is nothing forbidden or something like that.
Yeah, but still, no. Actually, no. There is some trade-off. Actually, what we want to get really is just there is some trade-off between epsilon and how many denominator we have between 2 to the k and 2 to the k plus 1. So
can I also ask another question? So because you said there is a strategy of the police, I asked whether it depends. Well, whether it's like an oblivious strategy or no, whether it depends on what the criminal does. You said yes because yes, because we add. It's like innocent that only cares about these intervals that already are played.
If we try if we add obstacles everywhere, then there's too many of them.
Maybe we can we modify this game maybe so that now the strategy of the police can be made completely oblivious, and just the requirement of the game that the police can add as many vertices as it can, but only 100 vertices above the current, where the current game is.
Okay, now of course we can allow police to add as many vertices, as many obstacles outside the path of the criminal.
Yes, I'm saying that because, and then because it will be clear that in what police does, it's just it marks all slowly marks all epsilon good vertices for more and more denominators in some order. then you just have to show that this strategy satisfies this requirement, that after if it does it in some little, well, I mean in some order, then it satisfies this requirement. But then it's clear that the strategy, if the criminal avoids all these things, then in the end this is good.
Yeah, okay. So you say that it's better to formulate lemma and the only only
just
third
to formulate the
vertical
game,
above
not like
the
that,
criminal.
but just above the criminal. Yes.
Yeah.
And then
So this lemma,
when you reduce, you just say we will consider a strategy of the police that is oblivious. It doesn't look what the criminal does. And what it does, it just marks in some order. Well, what's the point? That a vertex is good for some denominator. I mean,
for every
is a
for every
continuation.
denominator, we mark obstacles around all the multiples of some size. On the
Yes, but we do that, I mean, not all at once, because if we do it all at once, then we cannot avoid everything. We do it, well, we do it in some pace. Such that in the end, all denominators are considered. So all the obstacles are added.
And so the path should avoid all of them,
Yes,
Sasha,
but so that this first condition is true, but above the current criminal. And then
Sasha Kazachinsky, I think that you are right. We can assume that the police marks at the beginning all the obstacles, and then the criminal chooses the way avoiding these obstacles. But what Matthieu says, that this lemma about the criminal can be applied also to other problems. And it might be that for those problems, it's important that the police's strategy is not blind. Here,
not really. If you add obstacles, if you add obstacle all around the tree, then essentially you are not blind. You are adding obstacle depending on what the criminal does. So it's just a way reformulation of things.
Yeah. But I mean, I agree also. Yes. So, but somehow, you can mark all the all the obstacles in advance, but you have to somehow provide some property of that marking that guarantees you that it can cover anything, and that property is somehow formulated in that game. So there exists a way of drawing these obstacles such that when the depth is of the game, when the criminal already in the elf layer, we add only 100 vertices above it. So I think the game formulation also makes sense here. Because I mean, if I just mark all the obstacles in advance, how I argue that there exists an infinite path? To argue, yes, I need to say that there exists some way of putting these obstacles such that this property exists.
No, what do you say? Even actually all the obstacles can be placed at once in the beginning of the game, and then we are just proving that there exists a path by introducing.
I mean, it's just a reformulation of the theorem that there exists a number alpha that avoids all obstacles.
Right.
But yeah, we have. But then I mean, still the game makes sense. But it's just you're given a strategy that you say that this strategy in the end marks all obstacles, and it also satisfies this property number 1 above the criminal, whatever criminal does, right?
Okay, let me say like this. So we will, like in Baer theorem, we want to construct a sequence which avoids some doesn't belong to the union of some sets, and the sets are can be given in advance. Still, our construction is step by step because we introduce the set into consideration step by step. And the same thing is done here. We can make all the obstacle in advance, but just we need, when we prove the existence of a path, it's important for us that we consider only some obstacles up to some level, and add these levels synchronously with decreasing our interval somehow.
Yeah, but let me just say, you kind of agree with me, or you're trying to make an argument that I'm wrong in my.
But just no. I think that I understand what you're saying, but then I agree. But just say again what I should agree or disagree with.
I mean, I'm just suggesting a better way to present the same argument that would be, for me, like, would be easier.
So
to
what
understand.
is the better way?
So you're given this game, you're proving existence of the strategy as before. That's fine. Then you say, well, let's reduce the statement to the game.
Yeah.
And you say, okay, I will give, and then the game modified with this first condition, right? That the police can only add can make as many vertices as it can, but only 100 vertices 20 levels ahead of the current position of the criminal. Right? And still the same argument works that
But more or less, we can just even say, consider a weaker game. Just the claim is that whatever, imagine we create a set of obstacles in the beginning, but this set consists of layers, and obstacles of all layer number L have the following property, that on above they are all only start from L plus 20, and there is at most 100 of them above any given vertex of layer L.
Okay. Yeah, I agree. So, and then, but let me just finish. So how to reduce? Then you say, okay, well, in this initial game, we will give a strategy of the police that indeed in advance, it chooses all obstacles that will be marked. And these all obstacles are just exactly what is needed to prove the theorem, right? It's all, I mean, it's all so it's what a vertex is bad for some denominator if there exists a infinite path from that vertex that is epsilon close epsilon close to the multiple of that denominator. Oh, sorry, I mean, right? Sorry. I mean 1 over epsilon n close to that denominator.
So we can so the obstacles are made in layers. As L's layer contains, we consider the denominators of L's group, and we consider L plus 20 intervals, layer L plus 20 intervals that are epsilon close to the multiples of those denominators. That's if you say this is exactly right. Yeah.
So basically, and then you say the strategy of the police is to at step number, at the move number L, it adds all vertices that are epsilon good for denominators from 2 to the L plus 1 to 2 to the L plus 2.
And vertices corresponds on layer L plus 20.
No layers, just you add only these restrictions.
No, but restriction should be in terms of binary tree. So
yeah,
we should
you
decide
add all vertices such that for which there exists a continuation which is too close to some interval, to some denominator.
But all vertices of length L plus 20.
No, just all vertices.
No, if
but
we
you argue that there will be only 100 vertices at the level L plus 20 above the current node.
Yeah, but we cannot add a vertex of obstacle of length L. We need to add
Ah.
small intervals. We cannot just no. The real reason why we should do it is when we construct our path, we should not consider restrictions of corresponding to large denominator while we are fix only small number of digits. We should postpone it.
Okay. So you will guarantee that for every denominator on some level, you will mark all obstacles, right? And that's
Yeah,
enough to
yeah.
output then.
Yeah. And even
Yes,
even I
yes.
can say exactly the denominator of in the group number L is considered on the level of intervals of level L plus 20.
Yeah. So in the strategy of the police, you will show it doesn't eventually will mark all obstacles, but for every denominator there will exist a level such that all
Yeah.
continuations that might be bad for this denominator, too close to this denominator, will be marked.
Are obstacles, yeah.
Some
So
level.
avoiding this obstacle guarantees that we are good
Okay.
with
Yeah.
respect to this denominator.
Yes.
Yeah.
But then you can state the property. Well, when you give it like that, you can in advance state the property of the strategy of the police that you will achieve, and then it will be clear then that if the winning strategy of the is that if the criminal wins, then it proves our fear.
Yeah. No. I'm sorry. I mixed things. I should. It's very simple. What I create confusion just out of my bad preparation, bad stupidity. No, it is not. Nothing happens here really. It's just. Very,
But
very
now,
simple.
I mean, as a result, it seems we have more or less converged to a
So
good presentation.
what I hoped I convinced you that this solution of the Erdos problem is not really difficult, and it can be obtained easily, and even it has some common tricks with the results about pattern avoidance, Kolmogorov complexity, and so on. So the result of Kolmogorov complexity, there exists a sequence whenever a block of length n is large n, its complexity with respect to prefix is greater than 0.9n, something like this. So more or less this corresponds to this Levin's lemma. You have an infinite sequence when all large factors are almost random, 99% random, and even given the previous bits, but we just forbid things like this. Okay, any other question? Yeah, so I don't know. Maybe if Matthieu is still here and has a mic, maybe he can comment something, because it's he who told me all this, and so I am sorry that if I did not do the good job of presenting this argument, but at least maybe you can comment.
Okay, so maybe I can try to add a comment. So I'm not an expert on this problem either. The problem was mentioned to me by Jan Bugeaud, who does Diophantine approximation and stuff like this. And what he told me is basically that they had I don't know, 5 or 6 different open problems from the 70s, and suddenly in 2005 or something like that, someone discovered the LLL in their community, and they were able to solve, I don't know, 5 or 6 old open problem with really short proofs. But something about this proof is that it's not constructive, and well, we all know that there is this Moser and Erdos algorithm that makes things constructive, but now we have an infinite sequence, so it's slightly more complicated, right? If we want the number to be computable, then this is more complicated, and yeah, somehow this gives that if the well the sequence n1 n2 etc is computable, or maybe you need some extra condition, then you can actually compute the number alpha quite efficiently even, which is, I mean, it's not even trivial that you can compute it even using the LL.
Yeah, there is a special technique by Andrei Rumyantsev how to get something computable from LLL, but this is very, very, very inefficient. So no compute, no bound, nothing. It's just
I don't know
pure
if it
computability.
applies to this, right? I think you need at the degree of every bad event is bounded, right, to apply this technique.
I'm not sure. Maybe no. I guess that maybe it can make it working somehow, but I'm not sure. And even if it works, it doesn't give any bound for complexity, so it's not a but still if we have I don't know, if we have some kind of no, it somehow corresponds to, maybe the Lovász lemma is important if it's much more difficult if we consider, for example, for forbidden substrings, if we consider two-dimensional things, when something is forbidden in a two-dimensional word. But I don't know whether there is some analog of this two-dimensional question in terms of approximations and no, anyway, no, it's nice to have something computable indeed as a bonus, and with this strategy or potential, or even with this stupid strategy of criminal, it makes things easily computable, because we need to know only finitely many things which to avoid, and we can easily decide where to go. So we get computability just for free. But it's a bit strange. There is a huge gap between Dirichlet theorem, which uses all the denominators, and this counterexample, which requires denominators that grow exponentially. So something should happen in between, but I don't know what should we expect here.
But do we know something about measure of this alpha? I mean,
I
say
guess
that's possible.
the measure of this alpha, I think, is 0, because each time we delete some fraction, more or less epsilon fraction of all space, it's like in Lovász local lemma usually. No,
But
no, of course it's not rigorous, but if we take random alpha, that all bad events have probability epsilon, and they are approximately independent. So I guess to avoid them has a 0 probability. So this is not something which happens with positive probability, I believe.
There are still ways. I mean, so this is measure 0, but there are still many alpha in some sense. Like, I think you can consider Hausdorff dimension and stuff like this, which again I'm not.
To compute Hausdorff dimension, which is still positive. Yeah, for some d it should be non-zero Hausdorff dimension.
Yeah.
Yeah, still, even in this argument with criminals avoiding 10 steps later, we have some freedom, which creates things with a subtree with a positive Hausdorff dimension, I guess. So we get this, yeah. Okay, so that's any other comments, if or questions or whatever.
Now, maybe my own personal comment, but by the end of the talk, it all seems difficult and confusing.
No, then that's my fault. It's really, it's nothing happens. But sorry.
Oh, maybe, sorry, I guess I was also distracting too. I mean,
No. It was even worse. It would be even worse without. But still, I didn't draw properly. But too late. I think we should not organize improved talk.
But okay,
next
but
time.
is it written anywhere, either text or slides?
No, I guess I wrote some note when trying to understand the argument. I can send it.
Okay.
Yeah. Okay, so what do we have next time? Probably something better, but what? Sasha, do you planned some talks?
Well, on 9th, I hope there will be Starozhenko. Next week, I cannot be, unfortunately. I have to support my co-author on the other seminar. So
what should you do?
I have to morally support my other co-author on the other seminar. So,
Today you morally supported me, I see. And then you need to support some of the other people as well.
yes.
Yeah. No, really it's very useful. But
Then also, then also in the future, I also had like Valentina Delle Rose, who wanted to make a talk about infinite Eulerian paths, computability, but at least he explained me that some criteria for existence of Eulerian paths in infinite graphs by Erdos without any computability.
so
at least
it's a combination of infinite graph theory and abstract computability.
Yes.
And then you can classify this viral problem in some class and prove that it
unfortunately they don't mention this. I don't know. So
rainbow and they have a very interesting and very delicate classification. So there are rainbow theorem, there are Ramsey theorem with parameter n and k, and they are all not all different, but many of them are different, and it's very delicate and interesting thing. So I think Valentina should place his results in this general picture, because it's more like this.
Well, then it requires some work. Then we will try to do that work. But on 9 we might have Starozhenko just explain some communication complexity, result of computing rank of matrices, some application to streaming algorithms.
Yeah, okay, but any other plans for the next time when Sasha will be more or less supporting somebody else? Maybe some other volunteers to give a talk, or knowing someone who wants to give a talk. We still have. Cool. Do we have some students who want who learn something and want to give talk, or?
No, we cannot hear you.
We can skip next session.
Okay, we can skip, but still it's.
Саша, Шень, может, вы расскажете про эти голосования, там что-нибудь? Эти тоже, пока меня нет.
Ну, как-то это самое, я уже пытался что-то рассказывать, только запутал дело. Ну, хорошо, давайте поговорим. Ну, в общем, пока очевидной темы нет преследовать. No obvious suggestion for the next time.
Да.
Milovanov solved problem of Allender, and we should hear at some point, but I don't know. He somehow is now almost invisible.
Okay.
Okay. Then if something will be planned, we will send announcement. But if not, The next will be 9th, and Sasha will send the announcement soon. Okay. Thanks to everyone.
Thank you.
Bye.